All right. All right, we're a little late. Let's get going. So, guys, real quick. So, there's the breakdown. It ended up looking, I think, fairly comparable to the last exam. That's not a result of people dropping or anything like that. It was pretty much the same amount of people took. I think it would take maybe 5 or 6 students. So the breakdown's pretty much the same. Again, if you got above a 90, you should feel really good. If you got above an 80, you should feel pretty good. Well, it depends. It all depends upon what you guys are sort of shooting for. But you should feel pretty good if you're above an 80 and you've been above an 80 for both and you've done well on your quizzes. As long as you do okay on the final, you should be squarely in the A range. More along the lines of, above a 60 or so, or consistently above a 60 on everything, and you're sort of sitting in this sort of B range and so forth. I would say at this point, if you scored, below, I think probably a 40 on this, that's probably should be a little bit concerning. But at this point in the semester, I think we've got a couple weeks left. There's no real looking back at this point. You just sort of charge forward and do your best and try to identify the best ways in which case you can sort of put yourself in the best situation sort of moving forward. You should get your exams back. Those of you that had Friday, did you guys get it back on Friday? Okay, so at this point you'll be getting your exams back. I would say, again, there's really not too much time left. So just get me the regrade request form, and I'll go through them all. Try to get them to me, since some of you aren't going to get them back till Thursday. Which means let's just say by the end of... Get them back to me by next Wednesday. It's not this upcoming Wednesday, but the following Wednesday. And then when the class is over, I'll probably take a look through them. If there's any past situations of regrade requests that haven't necessarily been resolved yet, I know that there's a couple of you that are probably have sheets that are still staying in my, they're just sort of piling up in my mailbox, which is where I leave them so they don't get lost, because they'll get lost on my desk. So that's where they are until I do the next regrade batch. If you have any concerns about previous one, or if you filled one out that you think might have gotten lost, feel free to fill out another sort of just in case one if you're really concerned. But I know that there's 2 or 3 I think that I still need to deal with that I said I would deal with the next batch. So, but yeah, here it is. So we've got we don't have too much time left. I'll post this on the website so you guys can stare at it longer. But we have to sort of move forward. So there's really, sort of looking at the material that we have left. The 2 big topics that I sort of want to cover, and we'll see what we get through, is I'm probably going to spend today on amines. We'll see how much I can get through with amines today. I might be able to cover all of amines today, which would mean that next class we will be able to really get into organometallic sort of carbon-carbon bond forming reactions. So that's going to be something that's pretty important. Again, it's going to be fairly important in chemistry. 2 of the types of transformations that we'll learn have been recent Nobel Prize recipients because they're so powerful. So it'll sort of show you a little bit about more modern synthetic chemistry and some of the developments that have been made. And so I want to spend a class or 2 on that. So hopefully we can get through amines today. We'll see how we do, and then hopefully we'll move on to cross-coupling and sort of transition metal catalyzed carbon-carbon bond forming reactions tomorrow, or Wednesday. Okay, so we've talked about nitrogen, and so certainly when we discuss organic chemistry, right, certainly carbon and hydrogen are probably the two that we've seen a lot of, followed by sort of oxygen, and then nitrogen we've sort of touched on a little bit, but those real four elements are really the ones that make up the vast majority of sort of biomolecules that we talk about. So certainly sulfur, phosphorus, these are some others, but nitrogen is important within that regard. And so things like amino acids often have, well, they always have nitrogen in them by definition of the name and so forth. One of the interesting things about nitrogen that's sort of worth mentioning, and it certainly comes up in amide bond forming reactions, is something kind of special about nitrogen that I always think is worth kind of mentioning. So again, nitrogen, we have these lone pairs in our nitrogen system. So what's this functional group called? This is an amide, right? So amides or amides are again, very important functional groups. One of the interesting things about amides specifically, and this bears itself and comes out in some other chemistry that we'll talk about in a little bit, and certainly this is something that was probably discussed in previous semesters, right, is this idea that nitrogen, the lone pairs in nitrogen can oftentimes participate in a lot of sort of resonance structures, which is the one that I've shown you here, right? And the result of this is that nitrogen, we've seen this with oxygen as well, but certainly with nitrogen, an atom that would otherwise, we would think about as being, say for example, sp3 hybridized, becomes sort of sp2 hybridized, right? So, and it turns out that this actually comes up quite a bit with amides, is that you actually have what can be referred to as sort of rotamers, if you will. As sort of drawn, we have, it starts to behave more like an alkene, say for example, than say for example a ketone or something like that. So the nature of this is that it restricts the rotation around this bond to a certain extent, and so what can very often times happen, right, is that you can, within amides, if we have two groups here, or even if one of them is a proton, we can oftentimes get two what are kind of like stereo, almost like cis-trans type mixtures, right? Where in one case you could have this sort of R group sort of cis to the R1, and the other case you have the R group cis to S2. So this actually comes up quite a bit, certainly within synthetic chemistry. It's not all that uncommon for synthetic chemists to make an amide molecule, and what they'll see is oftentimes they'll see sort of an NMR that might look like it has two compounds in it. And you sort of look at it and you keep trying to purify it and nothing's happening, and sort of what you realize is that you actually in fact have these mixtures of rotamers. And they rotate fairly freely around that bond, but on things like the NMR timescale, they don't necessarily rotate that fast. So you can, in many instances, isolate this one and isolate this one, and within a matter of seconds, it'll go back to whatever ratio it was meant to go through. So that's just one sort of example that I think illustrates the importance of the lone pairs on sort of nitrogen. And part of this is tied into the fact that nitrogen, unlike oxygen, right? In the case of oxygen, it's really not all that important. In the case of nitrogen, the fact that nitrogen oftentimes has three things bonded to it often renders the nitrogen itself sort of, in some cases, pseudochiral, right? So this would be more cis-trans chirality, but certainly if you have molecules that look like right, if we just had, say, for example, a tertiary amine or secondary amine, there are these instances in which case that nitrogen can, in essence, have sort of point chirality at it, right? So all sort of becomes, the nitrogen itself becomes a stereogenic center, and in many cases that lone pair can sort of exist as an additional substituent. So it's not that all that uncommon for chirality to sort of exist in nitrogen, which is kind of one of the interesting things about nitrogen that we haven't perhaps discussed to date. This generally doesn't happen with oxygen most of the time because oxygen has two lone pairs, so inherently it cannot unless it's protonated and under extremely acidic conditions. Oxygen is not necessarily going to have point chirality to it. But again, nitrogen oftentimes can. But one of the interesting things about this sort of chirality to it is that that lone pair can actually do something that's kind of interesting, and that's that because it's sort of so small, and we've seen in cases in the past where it's planarized, nitrogen can, in fact, within itself, begin to become planar. So those lone pairs, and I always struggled really understanding why this is the case. And at a certain point, I just accepted that it was the case. But nitrogen can actually planarize itself, even in cases where we're not like this. And again, this is going to be a very high energy barrier, but the point of this is that those nitrogens, it can actually do what's called nitrogen inversion. This is just something else that's fairly interesting about this sort of nitrogen, is that those lone pairs can actually just by virtue of, you can sort of think about it sort of going through the nucleus, or the nitrogen equilibrating itself and moving around. This is one of the peculiar things about nitrogen. It doesn't come up too much, but it is something that I think is certainly unique about nitrogen. Again, nitrogen has point chirality, but this interesting aspect of those lone pairs being able to sort of go through this planar form and eventually end up at the other end means that those are very often quickly racemizable. So nitrogen, I think the point is that nitrogen can be chiral, so that's the important point to take into account. But in general, it's not oftentimes all that relevant, in large part because you can undergo this rapid racemization process, so it sort of renders itself sort of overcomplicates the system. So anyways, this is just called this is just sort of nitrogen racemization. It's just one of the interesting things that I thought would be worth sort of bringing up. Okay, so within the chemistry of nitrogen, we've already actually discussed a lot of chemistry of nitrogen just associated with other reactions, and certainly in some cases where, certainly in many cases where I felt that they were more closely related to other types of transformations. So if you were going to make, say, for example, a nitrogen-carbon bond, we've certainly learned how to do this. And so what's one of the ways that we've probably seen a couple ways that you guys can sort of remember to sort of make these. So if we wanted to make an amine, how might we make an amine? What is the way in which we've learned? We've really only learned one, maybe two ways to make amines. Yeah, so that's certainly the one that I was thinking about first and foremost. It's a reductive amination, right? So if you take carbonyl, right, and you condense it with an amine, right, you're going to get the imine, which can then be subsequently reduced, generally with sodium cyanoborohydride. this is one way in which we've learned to make an amine, and we can imagine doing this with and going to tertiary amine as well. We took it and treated it with another amine. So this is perhaps, you know, the fairly classic way to make. I don't want to say classic, but it's certainly one way to make amines. If we step back and just start talking more generally about nitrogen-carbon bonds, and then imagine how we might move from there, you can think all the way back to probably last semester when you guys first started learning about substitution chemistry, right? And if we were to take a nucleophile and treat it with an alkyl halide, right, we can then begin to make nitrogen-carbon bonds. The problem with, say, for example, treating generally an amine with an alkyl halide can be what, though? There's a couple problems. What's that? Say it again. Well, the one problem would be in a situation where you might get. There's a couple issues of taking an amine and treating it with an alkyl halide. The one is overalkylation, right? So the nitrogen is always going to have those lone pairs left behind, and so it can keep reacting, right, with that group. So you'll start to get, if you were to say, for example, try to make this R2, but instead make it with that secondary amine, and say, for example, an alkyl bromide. Right, you'll get some of this, you'll get some of the bis substitute, and you might even get some of the quaternary ammonium compound as well. So that's why we can't take our amines and treat them with that. You might imagine coming in with NH2 minus, for example, but the big problem there is that you'll very likely get things like elimination because it's such a good base. But we did learn about one at least fairly, it was probably one of the very early nucleophiles that we learned about because it's a really, really good nucleophile. And it's nitrogen containing, and it's I guess it's sp2 hybridized, but it's very linear in nature. I guess technically you could sort of think about it as almost being sp hybridized. What's that? I'm comparing cyanide, but that's not nitrogen-carbon bond. I'm talking about a nitrogen nucleophile where actually that's the nitrogen that's forming a nitrogen-carbon bond. Yeah. And N3 is an azide, right? So azides, absolutely. So azides, right, if you remember that the azide right? Azides are really good. So something like sodium azide. Again, in this case, the intermediate right? We'd make the sort of azido bond. And then one of the things that we could, for example, do with this is that we may imagine for example, reducing it. So different reductants, again, this is a sort of high oxidation state, so different reductants could reduce this. It turns out that I treat this with, I'm trying to think what the standard reduction is, but certainly something like LAH or certain reducing agents, probably metals and hydrogens would certainly be something that can reduce this, but under reductive conditions, you can begin to reduce that bond and get to systems like this. Right? The classic reduction of azides is something called a Staudinger reduction, which uses triphenylphosphine in water, but I don't think that's in the book. So, so just sort of standard reductions, lithium aluminum hydride. I think like zinc and HCl would do this as well. So there's a number of ways that you could do this. The one that we really haven't discussed, that's probably the other classic way to make nitrogen-containing molecules, is similar to this one here. It's called the Gabriel synthesis. Did you guys learn about the Gabriel synthesis? Actually don't have it in my notes. So what the Gabriel synthesis is because it's another classic way to make amines, again, that overcomes just instead of using an azide as your source. You can use these like succinimides. Okay, so this is going to be a much more easily depropionable nitrogen, so it's going to be fairly basic. It should be reminiscent almost of the sort of the diketo, right? So a lot of times when we have the 1,3 dicarbonyls, right, we can take those off under very mildly base conditions, and those are really good nucleophiles. So this draws a significant parallel to that, right? That this is going to be a highly stabilized nitrogen, because you can imagine the resonance forms in both ways. And so it's a fairly soft nucleophile, kind of like an acetate or something like that. So this will displace the bromide. This used to be highly used. I don't really see it used much in the literature anymore. And I think it's because of the conditions that are actually required to subsequently hydrolyze this. So the way that usually people... this is a very, very classic reaction. But I think that the conditions aren't people try to avoid them. So they often will use then hydrazine, and hydrazine will effectively react with this, effectively get both carbonyls. So you can imagine adding to the one and then adding to the other. You guys should probably be able to go through that mechanism. On your own, this could be a good mechanism problem for an exam. So why don't you try to figure it out on your own. Basically, hydrazine will effectively react with this, lead to those two molecules there. So that's probably a good mechanistic practice problem. So I won't go through it right here, but I think that's a good one for you guys to try to work out on your own.
It's called a Gabriel.
It's called a Gabriel synthesis. Yeah, if you want to look it up. Yeah, I'm pretty sure that's in your book. It's not in my notes, so but this is in every textbook ever. So it's a very classic. It should be in your book. If it's not, it would be the first that I haven't seen in there. But I'm pretty sure that should be in your book. But you can look it up if not. So again, it's just a classic way to make a nitrogen. So we learned reductive aminations. Azides would be another way. Gabriel synthesis is just another classic method. So certainly be familiar with those reactions and sort of feel comfortable with them. What I thought I would focus on more this class, because we don't have too much time left, is what can happen once you actually gain access to amines, and from the amine, so not necessarily synthesis of amines. I've just sort of shown two examples where we've seen in the past, and sort of one new one. But I thought what would be more interesting moving forward is what we can do once we have amines, because I think that they're fairly versatile compounds, and specifically we know one of the things about alcohols, right? We spent a lot of time this semester on alcohols, right? And one of the points that I wanted to bring up about alcohols is that they're fairly versatile, right? If you have an alcohol, you can convert it into an electrophile. So we learned a lot of ways to do that, right? You can turn it into a halogen, or you can turn it into tosylate, or something of that nature. And certainly they can often serve as nucleophiles as well, right? So certainly a nitrogen that itself, you can imagine, has a lot of nucleophilic behavior, and so it can certainly do that type of chemistry. But what I thought that I would focus on today is examples where nitrogen is basically turned into different types of leaving groups. And what we'll see is the ability to turn nitrogen into some of these leaving groups that we'll see, I think, provide some pretty, powerful properties and some certainly, let's just say, cool reactions. All right, so this is what we're going to focus on today is nitrogen. So we know how to make nitrogen-containing molecules. what can we do with nitrogen once we've made it is going to kind of be the focus of today. And what we'll start with is something that I think is kind of cool and certainly gets to this idea of stereochemical control, right? So, we've learned, and one of the very common reactions that have sort of been moving forward throughout our time in this course, right, is if we have a leaving group, say for example a halogen, there can oftentimes be some versatility here, right? So if we have that halogen, we can do a couple things, right, in terms of eliminations. If we want to get, say, for example, that alkene from a halogen, how might we get there? Yeah, like a bulky base. Terbutoxide was said. So certainly some bulky base, which is going to prefer to go with this position out here. If we want to eliminate in the sort of middle, though, right, what's going to happen there is that we are going to need some type of a smaller base, sodium hydroxide or something of that sort. And we'll get this sort of internal alkene shown here. Now, as you notice, the sort of way that I have this drawn, right, I'm kind of showing it as the potential to be either a cis double bond or a trans double bond. And the stereochemistry here, usually, all things considered, this is a situation where we in fact have 2 protons. Actually, let's do this real quick. We have time. So here's a molecule that has, and we'll just sort of move into nitrogen. This is just sort of a quick refresher on sort of stereochemistry. If I were to take this molecule, right, and I were to treat it with sort of a base that's sort of smaller, right, we're going to get one of 2 compounds. And we'll sort of discuss this really quickly. We're going to get one of these 2 compounds. And some of you will say, and you'll probably be right, although not necessarily for the right reasons, that you're going to get the trans one, right? And the reason why you might say that you'll get the trans one is because, why? It's lower in energy, right? And that's actually true. That is in fact the right answer here for many ways, but the product's not necessarily, it's not necessarily a thermodynamically driven reaction, okay? And so the reason that this may in fact go to the trans, you're not just necessarily looking at the final product. What you sort of want to look at is in fact the transition states that lead to these. And in this case, what we have, right, is 2 protons, one that we would call A and one that we would call B. And I just sort of want to reflect on this really quickly and sort of describe that it's the nature of which proton gets abstracted is ultimately going to be what's going to determine whether we get the E or Z double bond. Now, what is this type of elimination requires what type of geometry? Right, it requires antiperiplanar nature. So what has to happen is this bromide, right, has to effectively be anti, so it has to be on the other side and sort of coplanar to the proton. Another way to sort of look at this is to actually take a look at the Newman projection of this, right? So it's been a while since we've thought about Newmans, right? I was going to make a Seinfeld joke, but it would have been lame. Okay, so as drawn, if I were looking down this bond, right, I had the bromine to my left, I had the hydrogen, I had the methyl group going back. So this is HB, this is HA, and we have our R group over there. So this is the Newman projection of sort of what I have drawn, right? But in principle, again, bonds are freely rotating around here, so I can also imagine rotating that bond around. So as drawn, right, HB is anti-periplanar, right, to the bromide, right? And so if the elimination took place through this Newman projection, which product would I get? I get the trans, right? Because the R and the methyl group are on opposite sides from one another. The R group and the methyl group are on opposite sides from one another. Right? So this guy would lead to that one. But I could also draw the rotamer where the rotamer, I guess is fine, where the HA is over here. Right, so this would be if HB was anti-periplanar, right, with the bromide. And in this case, now the methyl group and the R group are on the same face as one another. They're going to be close to one another. So if it went through this one, we would get to the cis. So as you probably would have predicted, the trans would have formed. But the sort of reason why that is that the transition state, right, to get to that anti-periplanar nature of the proton and the bromine, this one is in fact lower in energy, right, than this one, right, because we have these Gaussian interactions between the methyl and the R group here. Here they're axial from one another. So it ends up being the thermodynamic product, but that's largely because in order to get to this sort of anti-periplanar nature, we want to go through the lower in energy compound. Now, this could certainly have effects if, say, for example, if HB was, say, for example, some group, right, that if it was no longer a proton, right, then there would really only be one stereoisomer that you could get to. Okay, so that's just the background, and this is what we would call sort of a syn elimination. Sorry, excuse me, I just got ahead of myself. This would be called an anti-elimination because the proton and the bromide are anti to one another. And what we'll see is that nitrogen, you can turn it into a leaving group or you can get anti-elimination. But as we'll find out, there can also be instances in which case you can get syn elimination as well. Okay, so we'll just start with one of these. Okay, so we'll just start with a very simple starting block here. And what I'm going to start with is just discussing, from a mechanistic standpoint, an elimination called a Hofmann elimination. Okay, a Hofmann elimination is again, a fairly classic transformation. Woodward used to use this a lot in his syntheses. What you do is if you take a primary or secondary or tertiary, whatever it's going to be, and you treat it with an excess of in this case I've shown as sort of bromomethane or iodomethane or something of that sort. What's going to happen here is that, again, you're going to keep alkylating this compound over and over until you get this quaternary ammonium bromide. Okay? Now, with this quaternary ammonium bromide in hand, if you simply take it and treat it to a base, as is sort of shown, you're really only going to get one leaving group here, right? You're going to get acetylene and in the day, you're going to get the trimethylamine, which will go out into the atmosphere to leave gas. Okay, so this is one type of elimination. So what's special about this class of eliminations? There's something that's slightly different about this leaving group than we've seen in the past. So in general, the leaving groups that we've seen have oftentimes been fairly, we're talking about halogens, about bromides, iodides. Some of our tosylate might be somewhat bigger, but this is probably, it's a tertiary three-dimensionally, and everything else, it's a very bulky sort of leaving group, right? And so this is just a sort of a standard elimination that you might imagine. But it turns out that if you have even situations where okay, so this is one type of elimination. So this is a case where if you were going to do an elimination, regardless of what base you use, because of how bulky the leaving group is, you'll always get, or usually always get, elimination to the more sterically more accessible alkene, or you'll deprotonate the more sterically accessible, regardless of what base you use. So any base, it turns out that in this case it's not going to matter sort of what you use. You're going to get the sort of kinetic, if you will, product in this case. And so this is one of the features about a Hofmann elimination. Now, trying to think of how I can sort of wrap these two together. Yeah. Say it again? So yeah, so generally, I don't want to say always, because there's always an opportunity where it might not. But the idea here is that unlike in previous cases where you needed a really bulky base, in this case you don't need a bulky base because the leaving group itself creates an additional steric environment that enhances the difficulty of deprotonating this other position. So Hofmann elimination will generally go to the sort of more open position. So it just becomes a very sterically big leaving group. I was going to try and tie this in with the next reaction, but the more I'm thinking about it, it may just complicate things more by doing that. So this is a special thing about the Hofmann elimination. So this is one elimination from a nitrogen. You can turn it into a leaving group, and then it becomes a leaving group for the less stable alkenes. Another elimination that I want to discuss, and then maybe I'll come back and try to come up with an example where this and the other one would sort of flip-flop. So this would be your standard elimination chemistry, unless you have, let's say, for example, an E1 elimination process. But I want to go back to that sort of idea that we discussed previously, which was sort of syn and anti-elimination. So if we had a molecule let's do this. I'm going to make this one R1, R2, and R3. Proton back there. So let's make this a gem dimethyl. So if we were going to have this dimethyl amines, tertiary dimethylamine, so we could do a Hofmann elimination, that's going to go the other way. But if we wanted to convert it and actually try to get the internal alkene, one way that we might be able to do this, right, and again, this this here actually. Let's do this. Sorry, I was trying to think about what. But this will be a good. We can do this on this. So if there's no adjacent protons over here, okay. If all we have is, say, for example, a phenyl group, and so we can't eliminate in that direction. If we were to go ahead and do a Hofmann elimination on this, what might be the stereochemistry that we would get, right? So the first step would be what? We take and we treat it to MEBR. So let's start here. Okay, that's going to make, and I've sort of drawn it very similar to what we drew before. And in this case, it doesn't really matter what we have over here. But you'll notice that now I've got the adjacent, the only protons that can eliminate here, right, there's really only one proton in this entire system, right? And that's going to be this proton that I've shown you here. As we sort of had shown previously, I haven't really changed much in terms of the stereochemistry here, but this, if we were to do a Newman projection of this, we could have a system where pH is abbreviation of phenyl. Right, this would be the only way that we could get an anti-relationship between these two, right? This is the only Newman projection that we can get. And so the alkene that we would generate through this process, right, would be the one where the phenyl and the R2 are going to be on the same side of the double bond, right? So once this eliminates, we're going to get an alkene, right, where the R2 and the phenyl group are going to be on the same side, right? And the phenyl group and the phenyl group, right, are going to be on the same side, right? So that phenyl group's going to be down. And so again, this is what we would call an anti-elimination. I keep doing that. Now it turns out that there's a reaction in the amine chapter here that I think complements this nicely. And it involves an alternative type of elimination. It's called a syn elimination. So instead of them being anti to one another, they become syn. So how do we do this? So this actually involves sort of some oxidation, sort of internal elimination. So it becomes an oxidation. So what you do is you oxidize this nitrogen, and there's a number of oxidants that you can use, MCPBA, for example. And what happens here is that you get an N oxide. So you've effectively oxidized that amine to basically nitrogen oxygen. So the nitrogen has a positive charge on it, the oxygen has a negative charge on it, so this is called an N oxide. What this creates is a system where you can actually do a 1, 2, 3, 4, 5. You can make this interesting 5-membered ring. Let's see if I can draw it in the best way. But this becomes your base. This is kind of where I'm going to get to, and hopefully it'll become clear when I draw it what's important here. But this nitrogen, as is shown, right, if that nitrogen were over here, right, if we want to have this is going to become our base, and that's going to deprotonate that, but that's too far away, right? So in order for this elimination to take place, instead of going through an anti-elimination, what's going to happen here is we're actually going to rotate around, and we're going to go through a syn elimination. So what we'll do is we'll rotate around this bond to bring this nitrogen basically, on the same face as that can draw a couple different ways. But now, if the nitrogen goes up, the phenyl group's going to go here, right? Which means the proton's going to go over here, right? It's that carousel. Everything in the back is going to stay the same. R2. The phenyl's going to be there. Okay. What's going to happen here now is that this oxygen is actually going to deprotonate that compound there. Okay, we're going to make the double bond, and then we're going to end up putting those electrons on the nitrogen. So it's what's called a syn elimination. So this is going to serve as the base, and then we're just going to get that same elimination process. So it's the same thing, it's just that we see up here, except that now our base is actually the oxide. Okay. So the result of this now, right, is now through the elimination process, the two phenols are now going to be on the same side of that alkene. Okay, and the product, or sorry, the byproduct, I guess, is going to be the hydroxylamine. Okay, does everybody see that? So this is, I think, a really cool, so we haven't discussed, we primarily focused on anti-eliminations, but this is what I think is kind of, when I was saying some cool chemistry, I think this is pretty cool, right? If we're under situations where previously, for whatever reason, we have this stereochemical control that necessitates anti-elimination is going to give us one stereoisomer, and we don't want that, here's another, at least, consideration that we can use to get to the appropriate stereochemistry. Yeah.
So what do you have to experiment out when you do this? Does it happen just like or does it even matter?
So yeah, so it's always going to go through the syn elimination. Maybe if we'll have time, we'll go over that later. But if we have multiple protons, then what you would consider is like we did before, right? Before there was 2 beta hydrogens. So it's generally going to go, because it's going to be thermodynamically driven. So if what you're talking about is 2 protons, it's going to follow the, sort of the more thermodynamic rule. So if you're talking about primary versus, if you're talking about a terminal alkene versus an internal alkene, you're always going to go to the more substituted alkene. Now, if you're talking about the potential of having a cis or trans, right, then what you'll want to do is you'll want to look at the Newman projections, because it's going to have to go syn, but you have to look at the 2 possible Newman projections of those 2 and just look at which one would be more stable. So what would likely happen is, as you've seen in the past, is that you'd probably get the thermodynamic product, because the transition state to that thermodynamic product is going to more closely resemble how it would be. But in this case, I've purposely stacked the deck so that there was one, just to show the sort of complementary nature of these 2. So again, this is a cool reaction. I'd like you guys to be prepared to predict stereochemistry in systems like this, right? So yeah.
What's its name?
So this is a Claisen rearrangement? Or Cope rearrangement, sorry. It's a Cope elimination. Sorry, Cope elimination. Sorry, so this is a Cope elimination. Okay. Okay, so we have about 20 minutes left. So I'm going to talk about one more reaction, and then we'll see what we have time, and I can go over some of this. But we're going to get through. It's really just these 3 things that I want to discuss today. I want to discuss Hoffman elimination. I want to discuss Cope elimination, and this one other that I think is really important. So, you guys remember about 2 weeks ago, I drew this molecule. You guys remember that? Anybody remember me drawing that on the board? See who's got a memory. Yeah, so who said that? Bonus points. So this is the benzyne precursor, right? I said here was a molecule that I that I made in lab, and it turns out that if you just gently heat this, right, what'll happen is some pretty cool chemistry will take place. You'll actually do an elimination of CO2, and you'll generate nitrogen as a leaving group, and what you will get to is a high energy benzene, right? So as we sort of discussed, this isn't necessarily an intermediate that we oftentimes want to make because we've put a triple bond into a 6-membered ring, forcing it to adopt a geometry far, far, far removed from what it would normally like to sort of adopt. The reason why this is able to happen, again, you usually trap this in situ, you have something else around it and it traps it, but the reason why you're able to sort of do this is in part because you have such a good leaving group here. You have nitrogen as your leaving group, and then again, the CO2 and the nitrogen sort of become gases. So you guys could probably all tell me how you'd make a carboxylate, right? Now the next question is, how might we make that nitrogen as a leaving group? And after you sort of learn this reaction, then there may be an opportunity to address how you might actually synthesize this molecule. So the question becomes, how do you synthesize how do we do this? Okay, and there's probably going to be a counter ion of some sort, right? X minus. So the way that we do this reaction is that we need a sort of a nitrogen-based electrophile. This isn't all that different from some reactions that we've kind of already seen to a certain extent. And that's that what we need is a really, really good electrophile that's ultimately going to leave. And in this case, what we're going to use is right. Hold on a second. And HCl. So you're basically generating HONO. So NaNO2. It's going to be this molecule here. And what we're going to do is we're going to take it and go ahead and we're going to treat it with sort of HCl. That's going to effectively protonate the system. What this is going to be is, formally, this is going to be a condensation reaction, similar to what we've seen in the past. So you might remember when we made things like, we've learned, for example, that if you, in the presence of an amine and a carboxylic acid, right, under eliminative conditions, you can basically take a carbon-oxygen bond, right, and then you can turn that into a carbon-nitrogen triple bond. And in many ways, that's what's going to be happening here, is that this is going to sort of in many ways serve as what we're condensing the nitrogen on. And what we're going to do is we're going to lose basically every possible equivalent of water from this system. Okay, so if we protonate this compound, okay, and we protonate it even further, okay, this is going to become a good electrophile. The nitrogen will be able to attack with this compound here, and what we will get to is we'll get to this nitrogen-nitrogen bond. Right, we're going to get to that compound there. So the mixture of these together, you're going to basically generate this electrophile here that's going to react with the nitrogen, And now what you probably notice is we've generated the nitrogen-nitrogen bond, and what we have, right, is two equivalents of water that we can kind of see on there, where if we can generate water and extrude water from the system, we can in fact get to this compound here. Okay, so how we would get there, you guys could probably sort of figure out, right? So what would be the first step of this elimination reaction? If we need to eliminate water, what's the first thing that we would want to do? We'd want to generate OH2+, right? So you'd probably get a proton transfer of some sorts. It wouldn't be intermolecular, but again, for pore space and everything, we're going to get this. Okay, from here, right, it should be fairly easy now for this to extrude water. Why? Because in addition to having a leaving group here, we have these lone pairs. They can help push it out. Right? And then we're just going to repeat that again, right? We're going to get a hydrogen bond transfer. That lone pair there again, and what we're going to do here is eliminate and get to our final sort of compound from there. Okay. So in this case, our counter ion is likely to be the chloride from a lot of the early chemistry. Again, we could probably have water extruded from this process, but again, it's once you sort of know what the electrophile is. It's simply a matter of making that nitrogen-nitrogen bond, and then after you make that nitrogen-nitrogen bond, what you'll notice is that you can, in essence, do you can basically do two dehydrations, in essence. So water can be left essentially twice. So this is the reagent. This is what you'll use to make that nitrogen leaving group. Why is this going to be valuable? Well, this is probably the best, as we sort of just illustrated there based upon Benzyme. This is by far the most willing to leave, for lack of better words. This is probably the best leaving group that we've seen to date. This is something that's driven by the fact that once you generate nitrogen, it's a gas, so it's going to render itself irreversible, right? It wants to take on those two electrons, and so this is your standard. This is like your this is halogen on steroids, right? So really good, yeah. I don't know. It's you're generating a. I don't know that it has. Maybe it has a name reaction. If it does, I don't really know what it is. You're basically making nitrogen as your leaving group. So this is in your book, in the nitrogen chapter. So once you know how to make these molecules, you can begin to do some really cool stuff. And the reason is because we start breaking from our standard halogen, because it's such a good leaving group. You can begin to do things that you would never imagine doing any other way. So if you, say, for example, wanted to turn this guy into, just to make sure so I'm not making stuff up. If you wanted to turn this, if you wanted to, say, for example, put a halogen there, for example, one of the things that you can do is just with a little bit of copper, and what do they have there? So like copper chloride and hydrochloric acid or whatever, I think the copper just sort of coordinates a little bit and helps it leave, and eventually what will happen is the counter ion will click back on there, but this is one thing that you can do. So again, if you want to put chloride or something there, these two things are maybe not the most interesting. You can actually take it and treat it with H3PO2 and actually get rid of it entirely. So if you need that there for sort of a handle, so this is actually a reducing agent, you can actually get rid of it. What's more important, so this is not all that interesting, but if you needed the nitrogen there as a handle to, say, for example, get some certain selectivity, you might find it useful. But what is important is that you can actually take this, it's such a good leaving group that you can actually take it and treat it with decent nucleophiles and actually get it to substitute there. So if you took this and treated it, if that was a halogen, say, for example, and you simply wanted to take it and treat it with hydroxide or something like that, or if you wanted to treat it with like cyanide or something of that nature, an acetate or something like that nature. If you had a halogen there, there would be no chance. It's not going to react. But this is such a good leaving group that you can take this and treat it with various nucleophiles. We'll just say KCN. You can actually do this sort of elimination. So again, to date we have not, and this still isn't going through necessarily the same type of, it's more likely going through, I'm not even entirely sure. You know, it's I guess it would be more similar almost to the Benzyme type mechanisms that we saw in terms of the fact that you're generating a almost carbocation-like phenyl compound, right? This is almost SN1-like in nature, and again, putting a carbocation onto a, on a center like that necessarily wouldn't be something that you would imagine wanting to do that much. It turns out that the other area where this can actually work out fairly interesting is if you remember, we did. You guys remember the Pinnacle rearrangement, right? So just a quick refresher on Pinnacle. Right, a Pinnacle rearrangement was basically one where if we took this molecule, right, we treated it to acid in acidic conditions, right, what's going to happen is we're going to protonate and ultimately generate tertiary carbocation center, right, and one of the reasons why Pinnacle rearrangement works is that you sort of need this carbocation-like character to it. And then what ends up happening, right, is that you do this migration. This probably is not going to work because of the fact that you need this carbocation character. You're probably not going to do this if the leaving group is on, say, for example, a primary carbon, right? So if you had something of this nature, right, and you treated these conditions, I'm not necessarily 100% sure what would happen, but more than likely, if you were going to do a rearrangement, it would probably be on this position over here, and even quite that, I'm not sure if that would work, in part because you'd have an alkyl shift from what's a primary carbon. But I don't know. But with the nitrogen, it turns out that you can begin to do these things because of the fact that generating a primary carbocation is now a little bit more feasible. So if you had a system like this, right, and you wanted to basically, if you had this, it would back under going. Okay, so you begin to get to these guys. So again, it should look fairly similar to the Pinnacle. I'm looking at this and so these 1,4 shifts can be kind of interesting because the hydrogen, sometimes you'll get hydrogen migration as well. This is what I have written down. I bet you the hydrogen could also migrate though. But the take-home point to this though is that you can begin to do these 1-2 migrations. Again, largely because this nitrogen is such a good leaving group that even though it's on a primary carbocation, you'd effectively be generating a primary carbocation. You can still imagine getting there. Yeah.
Do you know anything else with the CL only works if it's attached to an aromatic system, or does it work if it's just any R group with that?
I mean, we haven't learned any other ways, and so if you needed to use this, you would do those conditions. But you may be right. I'll have to take a look at it for you because these are the conditions that I know, and now I'm drawing an sp3 hybridized one. But as I was drawing this, I started looking at this, and I'm like, how would you make that under those harshly acidic conditions? You might imagine other things bad that are happening. So, yeah, these are the conditions that I know. I'll take a look at it for you. But for now, just assume that you can use them on any system. So, but I'll take a look because they do seem rather harsh for other conditions. All right, so we have only about 5 minutes left. So let me just review, I think, very quickly the reactions just to sort of summarize today, and then you guys can get going. So for the nitrogen chapters, again, this is, you'll certainly get some semblance of nitrogen on your exam. So what should you prepare for the exam, and what should you know? So I would say first, just refresh on how to make nitrogen-carbon bonds. Okay, and what are the ways, again, just refresh really quickly, what are the ways that we can do that? There's the reductive amination. These are things that we saw previously. There's the azide, alkyl halide, followed by reduction. Right, and then the one that we sort of introduced today is the one that comes from the succinimide, which is the Gabriel. Okay, so this is on making them, so you guys should know all of these reactions. And then in terms of using these carbon-nitrogen bonds, again, aside from, what we've learned already in terms of amide bond forming and things of that nature, what we really kind of focused on today was turning them to leaving groups. And the first one was a Hoffman. So again, just sort of a reminder, that's you take it and you treat it with with an alkyl halide or methyl bromide a few times to get to the quaternary ammonium, and then you do the elimination. What you guys need to remember from that is that it's going to go to the more sterically accessible proton because it's such a bulky leaving group. So there's not much room. It makes it much more difficult to come in and deprotonate the one that would lead to the more sterically congested alkene. So that's the Hoffman elimination. The Cope elimination. What I would like you guys, and what I'm in my bones, I feel like I'm going to probably end up asking is I really can't promise this, but I really want to ask a question on the final on alkene stereochemistry. Okay, I don't know that necessarily it's going to come in the form of the Cope elimination, but it very well could. But I'd like you guys to be familiar with sort of syn and anti-elimination processes, and really get comfortable recognizing that the protons need to be anti-periplanar in most cases, the Cope elimination being an example where that can kind of change, and you can do this syn elimination. So be comfortable with that sort of syn and anti-eliminations, and and that's kind of, I think, what's important for the COPE elimination. And then C, this idea of nitrogen as a leaving group. So again, know how to make it, recognize that it's a really strong leaving group, which allows you to do chemistry that perhaps you haven't done in the past. What we'll do on Wednesday is we're going to focus on cross-coupling reactions. So we're going to transition to that, because I'm anticipating that that's probably going to take 2 classes, and then we only really have 1 class after that. So I'm still sort of undecided on what we're going to do with the last class, because part of me wants to have a review class. So, all right.